All right, now on to some AP1. So, we got a block of mass M released from rest at point A. Then it's going to go down this hill, do a loop-de-loop, go up a little bit, and do another loop-de-loop. So this is definitely some energy and centripetal stuff going on. And this is my first time through it, so if I make any mistakes, feel free to correct me. But I'll give it my best shot. Okay. So all friction forces are negligible. That's important here. All right, what do we got? Oh, energy bar charts. Okay, very typical for AP1. Diagram A shows the energy bar chart that represents the gravitational potential energy, UG, of the block Earth system. Okay, so we're including the Earth. So GPE is totally allowed. And kinetic energy K when it's released from rest at the height 6r. So, released from rest at height 6r means that the total energy of the system is all gravitational at this point, and this is equal to 6 times mgr. And let's see, are there 6 bars here? That would be really nice of them if there were 6 bars. 1, 2, 3, 4, 5, 6. Yep, nice. Okay. So every bar can represent an mgr's worth of energy for us. So let's see what's happening at diagram B. So diagram B is where we're going to put it once it reaches the top of that first loop, which is a height 2r above the horizontal. So that makes sense, because if the whole thing is 6r and our loop has radius r, well, that means that B is going to be 2r above the ground. So that means that instead of 6 mgr's worth of potential energy, we're only at 2 mgr's worth of potential energy. So instead of going up to 6, we got to go up to 2. We don't need to necessarily label these, but it just has to be qualitatively accurate. I imagine we are going to have to do some math with this, so maybe it's helpful for us that this is 2 mgr. And then, even though we aren't given anything explicitly about the velocity, we know what it has to be, or at least we know what the kinetic energy has to be, because since energy is conserved, the total has to add up to 6 bars. So if there are 6 bars at the start, there have to be 6 bars at the end. So this would be 4 mgr. Again, it doesn't explicitly say we have to label, it just says that the relative heights have to match. So we have 6 bars, and then we have 2 plus 4. So they equal 6, and they're accurate with each other. All right. Starting with conservation of energy, derive an expression for the speed of the block at point B. Nice. Very classic. So we just want the speed at point B. So we got energy at 2 times. So we're just going to say that kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus gravitational potential energy at B. So we're at rest at point A, and our energy at point A from potential is 6 mgr, because it's mgh, but the height is 6r. Kinetic energy at B, we don't necessarily know what that is yet, because we got that unknown variable. And I should make my m's match here. And then plus the 2 mgr from earlier. So we can see that, as per usual, mass cancels, and we get 6gr equals 1/2 v at b squared plus 2gr. Subtract it over, we get 4gr is equal to 1/2 vb squared, which means that vb is just going to be the square root of 8 times g times r. Very standard calculation there. So again, we just set the energies equal. We know the height was 6r at the start and 2r at the end, so that's why we have GPE both times, and then we just do some algebra. You could also just do the shortcut that it's 2 times g times the change in height, so square root 2gh, but h is 4r in this case. On the following block on the following dot that represents the block, draw and label the forces, not components, that are exerted on the block as it slides through point C. So I'll draw myself a little replica here. So point C, if we go back to our diagram, is the top of the second loop-de-loop. Not that it matters which loop-de-loop it is, I guess, but so we're sort of fully upside down here. So first, of course, we have a gravitational force, mg, straight down. But then also, we are in contact with a loop. So it says it slides through the loop. So since it slides through the loop, that means that the normal force is not 0. So if it lost contact, then we wouldn't have a normal force, but in this case we do. And it points directly out of the surface. Again, the relative lengths don't matter here. If we had a grid, they would. So very carefully, we are just going to draw 2 downwards arrows on this figure. Using the correct setting would be nice. And again, it does not matter what their lengths are. I was just doing that to show some sort of a difference. So anything that is clearly the weight force, mg, is one of them, and anything that is clearly a normal force. Doesn't matter what you call these specifically, as long as it's clearly a force and clearly directly down here. And last, a student claims that 4r is the minimum height of point A such that the block can slide through without losing contact with the track after the block is released from rest. Briefly explain why the claim is incorrect. So it seems like this 4r is important here, so let's go back. So the student is claiming that in order to loop the loop, we need to drop this from a height of 4r. And the reason that's significant is 4r is the height of the second loop relative to the ground. So what they're saying is, I should probably just redo that. What they're saying is if we release at a height of 4r, we get to loop the loop. And well, as we probably know if we've done these problems before, just reaching the top is not enough to loop the loop. Because if you reach the top, well, that means the mgh up here is all the same as the mgh up here, which means you have no kinetic energy. So you just stop. So if the block is released from 4r, the block will stop when it reaches the top of the loop. Once it reaches the top of the loop, meaning it won't loop the loop. So that means the block will fall. Not looping the loop. There's another way of looking at this, and that's sort of a mathematical approach. So this is the more conceptual approach. It's just saying, well, if you release the block from 4r, it's going to completely stop when it reaches the top of the loop. And if you have no velocity at the top of the loop, and the net force is down at the top of the loop, it's just going to fall straight down at that point and not make it. The other way of seeing it is that At top, we have F net equals mg plus F normal force. And since this is a centripetal force, we'd say F net is mv squared over r is equal to mg plus F normal, which we're going to say goes to 0 at the point of minimum looping. So this means that V min at the top has to be equal to the square root of GR, which is definitely greater than 0. So you definitely need a velocity on the top to loop the loop because you have to get that centripetal force. Either of those should be good explanations. The first one, the more conceptual one, is definitely simpler though. All right, and now we'll go and do a suggested point breakdown. Again, I don't know anything inside, but here's my best guess as to where our points are going to be. So let's see, we're trying to add up to 7 points here. I bet the energy bar chart is just going to be 1 point. It's pretty straightforward. So to get the point, you have to make them, both bars have to add up to the 6 MGR, and they have to come in this relative ordering. So I think this is the only solution. Again, I don't think you have to label it, but you just have to have 2 bars here and 4 bars here. Then this energy conservation thing I imagine to be 2 points. So we'll get an answer point and some attempt of equating energy at 2 points. Free body. I bet it is just 2 points, 1 per force. I could be wrong, but we probably get 1 point per force on this. And then for the justification question, I imagine this is definitely 2 points as well. So again, it's going to depend on the explanation. You probably get a point for indicating some reasoning as to why the block needs more velocity to loop the loop. So I'll actually make a connection here and say that H min has to be greater than 4R. So V top is greater than 0. That might be required. You might have to say that you need to drop it from a higher height than 4R so that your velocity at the top is not 0. I don't know if they'll accept that that's being implied or not, so I'll just explicitly say it on my second run through here. So I think we get some sort of point for indicating that the velocity at the top is 0 in this case, and then you probably get another point for indicating that just getting to the top isn't enough. You need more velocity than 0 at the top to actually finish the loop. So that's my guess for point breakdowns. We'll see in July how close I was.